Welcome to the Introduction to Model-Based Quality, or MBQ, our connected product portfolio for GD&T design and realization from Siemens. In this session I will first quickly talk about how model-based quality can help manufacturers digitalize their dimensional management practices and achieve profitable quality. I will then introduce our latest addition to the MBQ portfolio, NX VSA. We will use a simple example to demonstrate the complete process of GD&T design, optimization and inspection programming using NX MBD, NX VSA and NX CMM to show a true end-to-end NX for MBQ story. Let me start with two real-world stories. First, in 2016, after introducing a new smartphone, the manufacturer had to recall 96% of the 3 million phones sold in the first 3 months. They lost over $6 billion in this process. The root cause, according to a 4-month-long investigation, was irregular-sized batteries. The speculation was that the phone itself didn't leave room for the battery to expand, which led to a short circuit. The other story is about a car manufacturer who had to recall over 9 million automobiles in 2009 and 2010 for fatal crashes due to sticky pedals. They lost over $2 billion in this process. The technical fix to this problem was to insert a Canadian dollar coin or a shim with similar thickness behind one of the teeth components to reduce the excess friction. As you can see, both stories have to do with a problem called manufacturing variation, also known as dimensional variation due to manufacturing. It is the deviation between the physical piece and its digital design. Manufacturing variation can directly impact a product's quality in its function, assembly process and appearance, often causing scrap, rework, production delays, and warranty costs. The engineering and manufacturing disciplines use geometric dimensioning and tolerancing, or GD&T, to explicitly describe nominal geometry which is theoretically perfect, with allowable variations or tolerances. Although GD&T can accurately communicate product and process requirements, use of GD&T requires some level of discipline to assure proper interpretation. Perhaps the first instance of this discipline came about during the first industrial revolution over 250 years ago, when Eli Whitney basically started a way to communicate dimensional requirements when he invented the cotton gin and interchangeable musket components. This has evolved over time to become what we call dimensional management. Dimensional management is a quality engineering discipline for GD&T design and realization, through optimized part tolerance design, robust assembly process planning and controlled manufacturing variation. It spans the entire quality life cycle, with defined processes and deliverables, to arrive at a fine balance between the cost of good quality and cost of poor quality. For the purpose of this session, we'll simplify the definition of a quality life cycle by starting with advanced quality planning such as APQP, followed by design for quality, inspection planning, build for quality and customer quality assurance. Model-based quality plays a significant role in this life cycle and is our solution for digitalizing dimensional management. It's a bridge that connects design intent and data-driven activities in delivering shop floor quality. Model-based quality has multiple stakeholders, including design engineers, manufacturing engineers, tooling engineers and quality control engineers. The entire D2MI process, or design to manufacturing and inspection, which focuses on 4 use cases: GD&T design and validation, PMI and management, inspection planning and programming, build quality validation and control. Model-based quality solution is a portfolio of tools for upgrading to dimensional management 4.0. We have VIS-based VSA and NX VSA for GD&T design and validation, NX MBD and PMI manager for PMI and management, DPV, NX CMM and BCT for inspection planning and programming, and DPV and VIS VSA for build quality validation and control. Now let me show you how MBQ works. It first starts with the virtual product. In 3D model or 2D drawing, VSA then virtually fabricates parts according to its GD&T design. Assembles these parts together per real assembly processes, and then produces and inspects large numbers of such virtual assemblies to verify and validate part and assembly GD&Ts, and identify critical to quality PMIs to limit manufacturing and inspection asset costs during real production. This is a highly iterative process between design specification and engineering verification, until the product design including geometry and PMI are ready for release. Once the design is released, all downstream activities become sequential and straightforward. First of all, PMIs are extracted into Team Center for Lifecycle Management and Manufacturing and Inspection Planning using PMI Manager. Then CMM programs are generated directly from the master model and simulated for optimization using NX CMM. Now it's time for production execution. Parts are cut and fabricated, and inspected, all by running CNC and CMM programs previously created from the master model. Measurement data of real products are collected from the shop floor to provide real-time quality reporting, analytics and dashboard using DPV. As you can see, the design intent master model including CAD and semantic PMIs flows from design to downstream processes, and back from as-built quality data. The difference between the two is the manufacturing variation that MBQ tackles. The truth is that most of our customers are already doing some level of the 4 use cases of model-based quality, but often in a disconnected way. With our MBQ PMI integrity and interoperability component, there is no disconnect as it breaks down the walls between the stakeholders, enables cross-value stream communication and collaboration, and closes the quality loop. In addition, Teamcenter connects and enriches the quality digital thread of PMI from design to realization and beyond. In conclusion, model-based quality is a complete end-to-end solution from design to manufacturing and inspection. It is effectively driven by PMI interoperability and integrity, and its deployment is scalable through plug and play on the PLM digital backbone. The bottom line? Model-based quality digitalizes dimensional management for GD&T design and validation and helps manufacturers achieve profitable quality. Now, let's talk about variation analysis, also known as VSA, the engineering tool in our model-based quality portfolio for designing and validating part and assembly GD&Ts. It does so through tolerance analysis and variation simulation. Tolerance analysis or stack-up study is an engineering method for understanding how the variation of individual part geometry features and the variation of their assembly process contribute to higher-level key product characteristics, also known as KPC. Those top contributing variations are identified as critical to quality factors, also known as CTQ, and are to be closely monitored and controlled during manufacturing. Therefore, the CTQs are also often referred to as key control characteristics, or KCC. Variation simulation is a computerized method for performing 3D tolerance analysis and optimization through Monte Carlo simulation of part tolerance fabrication, assembly tolerance stack-up, and KPC tolerance measurement. VSA input includes 3D models, initial GD&Ts, assembly process, other dimensional variation factors such as deflections and deformations, as well as KPC measurement requirements. The 3D models for VSA could be from many different CAD platforms through the JT format. The initial tolerances could be from company design guidelines, standards, or empirical data such as metrology data and experiment findings. The assembly process includes both assembly sequences and locating methods. The KPCs could be from design requirements, manufacturing experiences and lessons learned, and other quality activities such as Six Sigma studies, failure mode and effect analysis, also known as FMEA. VSA output includes KPC performance and KCC contributor report. The KPC simulation results can predict KPC variation and quality percentage rate from product design and assembly process planning, and the KCC contributor reports can list and rank all contributing tolerances or manufacturing variations, and identify top contributors for design improvement and manufacturing focus. GD&T design using VSA is a highly iterative process between design specification and engineering verification, until the product design including geometries and PMIs are ready for release. There are 2 VSA platforms, the VIS VSA on the Teamcenter visualization platform, and the NX VSA on NX. VIS VSA is our flagship variation analysis tool with extensive modeling and simulation capabilities, including kinematic and flexible assembly operations. NX VSA is a new NX native design tool intended only for design engineers to design and validate part and small assembly GD&Ts. NX VSA provides standard VSA capabilities such as static assembly operation and standard measurement operations. NX VSA models can be imported into VIS VSA to be part of a larger assembly. NX VSA is first available in NX 1926 release. Now let's see a NX VSA demo to understand how it works. So, let's use this assembly to show how NX VSA can design and validate the GD&T of a very simple part, a block with a hole and a slot. The assembly is a simple configuration of 3 instances of the same block part, assembled together using a fixture of 1 plate and 6 pins. The goal is to make sure when the left and right side blocks are put on the fixture, there is sufficient yet not excessive distance between the two so that the middle block can be inserted in between, and fit in nicely. Therefore, the key product characteristics or KPC here is the gap variation between the left and right side block. The first step is to open the block in its own window to check on its initial GD&T design. You can see there are already some GD&Ts on the part, but missing datums and some other tolerances. Let's add the datums first. One way to add GD&Ts in NX is to directly use the NX PMI module. In this case we can pick the datum feature symbol function from the tool ribbon. As you can see, the dialog window is quite comprehensive and overwhelming. You would have to make a lot of decisions not necessarily relevant to the creative part of this task, such as to decide where to place the symbol, in what coordinate plane, where to terminate the leader line, how to associate it with a feature face, and how to stack it to other tolerances already applied to this feature face, and so on. Thankfully, NX now offers a new tool starting in NX 1953, called NX MBD, to make annotating GD&Ts much easier and faster. Basically, it's a new capability to create a bunch of logical rules that customize NX PMI function dialog windows to fields only relevant to the creative part of adding GD&Ts. NX MBD comes with some out-of-box rules. You can also create your own rules. Now, let's use the out-of-box rule to create datums. You can see there are 4 rules here, with mouse over description prompts. We will use the last one to create all 3 datums in one shot. First, let's select the bottom face for datum A, then the whole for datum B, and the slot made of 2 plain faces for datum C, and done. You can see 3 datums created, associated with their respective faces, and stacked to existing tolerance annotations. Now let's add orientation and position tolerances to the hole and slot. You can see there are other out-of-box rules, but this time, I'm going to use my own rules. This one is to add feature control frames, or FCF, to existing dimension callouts. Select the hole dimension and the slot dimension, pick the tolerance type. If the type is not on the list, you can later edit the PMI annotation or the rule itself to add the types. I will delete the B and C datum reference here since these are the datums themselves. Let's keep the MMC and change the value to 0.25, and then click OK. Again, GD&Ts are created, associated, and stacked nicely. Now I can change the datum B tolerance type to perpendicularity, without having to worry about the rest of this overwhelming dialog. Now let me change the datum C tolerance to, change the value to 0.5, add datum B reference and with MMC. That's it. Let me quickly change this to 0.25. So, now we are ready to use VSA to validate and improve this initial GD&T design. Let's go back to the Assembly tab. Go the Application, under Manufacturing More, here is Variation Analysis. This opens a new navigator for VSA, starting with an empty process. You can see all GD&T PMIs are turned on in the 3D workspace. Now right-click on the process node, and select Create Model. What this does is basically pull the entire assembly into the VSA model. You can resequence the items by drag and drop. I'd like to arrange my 3 blocks in the sequence of left, middle, and then right. Now let's look into each part, and you can see all features with GD&Ts are already automatically created under each part, including datum symbols and tolerances. You can turn on or off these GD&Ts in the 3D workspace. Now, we are ready to create VSA assembly operations to locate the left block and the right block to the assembly fixture, according to the assembly process, including the sequence and locating methods. Let's first set up some simulation preferences. We will simulate producing and inspecting 2000 assembly builds. HLM simulation is to generate contributor reports, set offset parameters, and turn on some parameters for simulation reporting. We'd like keep 2 decimal digits, and we want to see all contributing tolerances listed with 0% cutoff. Now we are ready. Right-click on the assembly level node, select Add Assembly Operation to open the dialog. First, let's give a name, Assemble Left Block. And then pick from the process tree the left block as the object to be moved, and then pick the assembly fixture as the target the block to be moved to. Click the plus sign and you will see NX VSA is smart enough to detect possible locating constraints you might want to use for this assembly operation. Let's make sure of it. Clicking on the first pair highlights the mating surfaces at the bottom of the block and top of the fixture. The second pair is between a fixture pin and the datum B hole of the block. The third is between the fixture pin and the datum C slot. By now I think all 6 degrees of freedom of the block are all constrained. The fourth pair seems to be between the slot and the other pin. If the 2 planes of the slot are considered unbound, this constraint might be possible, but not in this particular case, so we will simply delete it by clicking on the X. It's always easy to delete than adding. Here you can see the pair number in the first column, and constraint type is not defined yet in the second column. Click on the Assembly Operation Validation button to validate the math behind it, and you can see the validation is successful, and the constraint type is also determined for all pairs. In this column, the red check marks show that float tolerances due to the clearance between the pin hole and pin slot sizes are turned on. Double-clicking them can turn them off, for instance, in the case of press-fit or tapered pins. You can also resequence the constrained pairs by clicking the up and down arrows, to reflect your true locating conditions. You always need to validate after modifications. You can now click OK to finish and exit this dialog, or click Apply to finish and start creating another assembly operation. We are now going to move the right side block to the fixture, in very much the same way. Name it, pick the object and then the target, add, check, delete unwanted constraint pairs, validate it, and then done. As a best practice, I'd always like to move the assembly operation to be right after their respective objects in the tree, for easy read of the model. So now, we are getting ready to create a measurement operation to measure the distance between the left and right side blocks, but first of all, we need to create two measurement points. Double-click the right side plane of the first block to bring up the feature property dialog, select creating individual points, let's create a point on curve or edge, pick the edge in the 3D workspace, click OK and then OK, and a child point is created, an inspection point. Now let's create a point on the left side plane of the second block in the same way. Double-click the feature, add individual points, point on edge or curve, pick the edge, and then OK and OK to complete the task. Now, right-click the assembly node, select Add Measurement Operation to open the dialog. First of all, let's give a name to this operation. Here you can see a list of measurement types available in NX VSA. We are still adding more to the list. We are going to use the gap flush measurement for this one. Let's pick the first inspection point and then the next one. As for the measurement direction, let's use Y, so we'll pick YC, and this calculates the nominal distance to be 75 mm. Now let's define the tolerance limits for this distance that will allow the middle block to fit in nicely. We will use plus and minus 0.3. Here is your measurement. We are now ready to run simulations. Right-click the process node and validate the model first, to make sure all the logics and math behind the scene are good. Here is a validation warning saying the middle block is not assembled to anything yet. It's fine for now. Now right-click the process node and select Simulate Model. 2000 simulations of this simple assembly takes almost no time. It's done, and let's take a look at the results. First, the summary table for this measurement shows the parameters I selected when setting the simulation preference: nominal, standard deviation, percentage out of spec. Right-click the measurement operation itself to open the simulation result page. Here you can see the simulation result distribution curve. Tails on each side outside of the upper and lower tolerance limits are showing red. You can see all the statistics below the curve. This is very much the same as the VSA process report. Over 7% out of spec. Doesn't look good. You can scroll down to the C contributor report to understand the contributing tolerances and focus on the top contributors for design and process improvement. Looks like there are 4-way tie at the top, each at 15.3% contribution effect. The first two are the two assembly operations, probably because we enabled float tolerances. The next two are the surface profile tolerances of the two planes this gap measurement is taken between. Clicking on the contributors in the list turns on the features in the 3D workspace. It also highlights the features in the VSA process tree. The next two higher ranking contributors are the datum reference schemes, probably due to bonus tolerances from the maximum material conditions, or MMC. Okay, let's focus on fixing the top contributors first. With the assembly operations, let's go to turn off the floats, meaning to request press fit or tapered pins for the fixture. Let's find the first assembly operation and double-click the floats to turn them off, validate and then OK. Then do the same to the second assembly operation, open the operation, turn off the two floats, validate and close. Now let's run 2000 simulations to see how much it has improved the gap result. Follow the same steps, validate the model first and then run simulation and review the result. You can see there are still red tails, but out of spec. Is reduced to 5.75% from over 7%, and the two assembly operations are no longer the top contributors. Now let's work on the new top two contributors, the surface profiles of the two measurement planes. You can also scroll down to see the contributing tolerances since we set the cutoff to be 0%, but let's focus on the top contributors. Let's go to the block part, and change the surface profile tolerances of the two planes to 0.3, of course this tighter tolerance must be confirmed by management for manufacturing capability and higher cost. This is a cost of quality. Now let's switch back to VSA, and you can see these two tolerance changes are already reflected here. This shows VSA is a true native app to NX. Now let's do another 2000 simulations to check on the result improvement. You can see the gap variation is further reduced, and now the out of spec is less than 1%. The result now looks much better, and the top contributors now are the two datum reference schemes, because of the MMC bonus tolerances. To fix that, we can either tighten the size tolerances of the hole and slot, or do not allow MMC. Again, let's go back to the block part, and take away the MMC modifiers. Now let's do the VSA simulations again, validate the model and then simulate 2000 runs. And now the out of spec is less than 0.2%. You barely can see the red tails, and the top contributors now are back to the already reduced surface profiles. Fixture pin tolerances are also bumped up in ranking. This shows that we are pretty much done with optimizing both the block part GD&T design and the fixture design. One more thing, we now need to add those otherwise unspecified tolerances to the 3D model for them to be used in some downstream applications, such as first article inspection. Once again, the newly available NX MBD can do the magic here. I am using this rule to create a default surface profile on all untoleranced faces. You can see 5 additional faces are now toleranced. I can still go in there to edit the tolerance, say to add datum references A, B and C. Now the block part with validated, optimized, and fully annotated GD&Ts is ready for release to downstream applications, such as generating 2D drawings, creating inspection plans, creating CNC and CMM programs, design tooling, and so on. Unlike the PDO file in VSA, NX VSA does not have its own model file. Its model is saved together with the assembly PRT file, and can be easily used in the Teamcenter managed mode. Now that we are here with a true MBD model, we are taking it up another notch. Let's quickly create a CMM program directly from it. We are going to use this Wenzel machine. Extract PMIs to get all the GD&Ts from the model and generate probe paths. By the way, all these steps are shown in much more details in our NX CMM introduction session. Please go check out that session if you'd like to learn more. You can see probe paths are generated for all tolerances, including those otherwise specified tolerances. We can then add some part alignment such as a teach point. Resequence the paths. Set up collision avoidance. And now we are ready to run simulation. The machine will pick up the right probe from the rack, and start to touch off all the tolerance faces. You can see sometimes during the simulation the probe arm color tuned orange, indicating range limit violation. In this case the controller head is too close to the table, meaning I'd need to further raise the part using some sort of standoff pins or fixtures. We'll skip this step for this demo, and go straight to post-process the program to, say PCD-MES. Here you can see the CMM program. This will conclude this demo. In conclusion, as you have seen in the demo, from initial GD&T annotation in NX PMI, to GD&T stack-up simulation and optimization, to GD&T inspection programming, the entire GD&T PMI integrity and interoperability workflow is done within NX. All dataset and deliverables can be managed in Teamcenter. This is now a true end-to-end NX for model-based quality story. Thank you very much for attending this MBQ overview session. Please feel free to contact me if you would like to learn more about model-based quality, NX VSA, or any other MBQ component tools. Thank you.